my previous lecture, I started with a modern extraction technique, that is pressurized solvent extraction, which is also known as accelerated solvent extraction or superheated liquid extraction or subcritical solvent extraction, and so on and so forth. In that, we discuss about the basic fundamentals and principle of the extraction technique, that is how it enhances the yield of the extraction or enhances the yield of the secondary metabolites that have to be extracted from the given matrix. We also discuss about different modes of pressurized solvent extraction like static and dynamic mode. Then we discussed about the instrumentation aspect of this technique and what are the steps involved in static as well as dynamic mode, what type of equipments are involved in static and the dynamic mode. So friends, in continuation with my previous lecture, today I am going to start with the parameters that can affect the overall efficiency of the accelerated solvent extraction process or the pressurized solvent extraction process. Now, if we look into this image, I have basically categorized these parameters into different headings, like the parameters that define the characters of the matrix, the type of the extraction or the solute with which we are dealing, or the extraction mode of PSC or ASC, factors affecting the overall extraction process, and the additive or the extraction enhancers if they are being used during the extraction process or not. But for our convenience, I have penned down certain parameters irrespective of their category, like temperature, pressure, solvent, addition of additive, solvent to feed ratio, composition of the sample, particle size, and the extraction duration. Now we will discuss these parameters in detail. So coming on to the temperature. Now as we increase the temperature during any extraction process, we have observed that temperature enhances the overall extraction efficiency. Now in case of pressurized solvent extraction or ASC, if you increase the temperature, and we know that the enhancement of temperature is far above the atmospheric boiling point of the solvent. So when we boil or when we heat the solvent above its boiling point, obviously under enhanced pressure condition which allow the solvent to remain in the liquid form, the enhanced temperature influences the kinetics of the mass transfer of various solutes which are present in the matrix. Now we know that the solute molecules, they have certain kind of interactions within the matrix, and this enhanced temperature basically helps in overcoming those solute matrix interaction, and they allow the solubilization of the solute molecules in the solvents. And further, this increased temperature also helps in decreasing the energy that is required for the desorption of the solute molecules which are adsorbed on the matrix surface. So we can say that if you increase the temperature, then obviously the solute matrix interactions get disrupted and the solute is now free to get solubilized in the solvent. Vis-a-vis, it also decreases the energy that is required to dissolve the solute molecules. Further, the enhancement of the temperature also causes the delay in the attainment of equilibration between the solvent and the solute molecules. Because if you increase the temperature, the solubility power of the solvent increases, that is, it can solubilize more solute molecules in a given volume. Whereas under normal or atmospheric condition, the solvent easily get saturated because there is an equilibrium that is attained between the solute and solvent, between the concentration of solute in solvent vis-a-vis the concentration of solute in the matrix. So this equilibration or attainment of equilibrium is delayed when you increase the temperature. Now increased temperature also decreases the viscosity of the solvent, which we have discussed in the previous extraction techniques, and this enhancement of the temperature as it decreases the viscosity, this decreased viscosity helps in increasing the diffusion of the solvent into the matrix. This is one aspect decreased solvent viscosity. So I have taken an example of 2-propanol, wherein when the temperature of the solvent is increased from 25 to 200 degrees Celsius, the viscosity of propanol decreases 9 folds. So this is the effect of increasing the temperature above the atmospheric boiling point. So as I told you that when you increase the temperature, the viscosity of the solvent decreases. As the solvent viscosity decreases, now the solvent can easily diffuse into the matrix, and since the increased temperature has increased the solubility power of the solvent, it will solubilize the solute molecule, it will dissolve the solute molecules which are adsorbed on the surface, solubilize them, and because of this decreased viscosity, this solvent which has solubilizes the solute in it will be easily diffused out from the matrix also. So diffusion inwards and diffusion outwards both are facilitated by increasing the temperature. And it has been observed that whenever the temperature increases from 25 to 150 degrees, the diffusion of a solvent increases by 2 to 10 times. So this is the major effect by which the extraction efficiency increases. Further increase in temperature also decreases the surface tension of the solvent. And once the surface tension is reduced, the matrix or the solvent becomes more efficient in making contact with the matrix, in causing wetting of the solute molecule, wetting of the matrix particles, thereby increasing the overall extraction yield. Apart from all these effects, decreasing the viscosity, decreasing the surface tension, enhancing the solubilizing power of the solvent, increased temperature also causes the change in the properties of the solvent. And if I want to explain this, then say for example you are using a polar solvent, and that polar solvent obviously by a journal chemistry rule will be able to solubilize polar constituent in larger quantity. Now it has been observed that when you increase the temperature beyond the atmospheric boiling point, the properties of that solvent changes. And this change in properties is largely due to the decrease in dielectric constant. And with the increase in temperature, the ability of the solvent to solubilize less polar or non-polar constituent also increases. So I have taken an example of water. We know that water is a highly polar solvent, and water is known for solubilizing the polar constituents, whereas it is not able to solubilize the non-polar constituent. So as you can see in the diagram, whenever the temperature of water is increased from 100 degrees, which is the atmospheric boiling point, to 200 degrees Celsius, almost double the atmospheric boiling point, the water has similar kind of solubility properties as that of methanol. You further increase the temperature to 300 degrees, water has similar kind of solubilizing properties as that of acetone. You further increase the temperature to 400 degrees Celsius, then water has similar kind of solubility properties as that of dichloromethane or chloroform. Now as we are increasing the temperature, the nature of the water is changing towards non-polarity. If we further increase to 500 degrees Celsius, then water has solubility characters similar as that of the hexane. So obviously when we are increasing the temperature above the atmospheric boiling point, we have to increase the pressure to the optimum level so that we are able to keep water in the liquid form. So we prevent the phase transition of the solvent by increasing the pressure. So this is how basically when you increase the temperature with subsequent or with the parallel increase of the desirable pressure, you are changing the properties of the solvent, and at an appropriate temperature level you can even use water to extract out the non-polar constituent, which is not possible when you are doing extraction with water at the atmospheric pressure. But increase in temperature is always not useful. Many a times it has been observed that if you increase the temperature above the optimum level, then it may cause degradation of certain thermolabile constituents or thermosensitive constituents. And in such cases one has to be very critical in optimizing the temperature condition during an extraction process, because our main aim is to extract the solute molecules, and if by increasing the temperature in order to enhance the extraction efficiency, we are causing degradation of those solute molecules, then the whole process becomes non-futile. And therefore, optimum temperature conditions have to be maintained, the temperature conditions have to be optimized for extracting a particular matrix, and this optimization varies from sample to sample, and the effects of sample or the matrix we will discuss ahead. By and large, it has been observed that for natural products, the optimum temperature has been found in a range of 100 to 200 degrees Celsius. And generally, for majority of the natural product samples, 160 to 180 degrees Celsius temperature range has been found to be most appropriate. But yes, I repeat again, we have to optimize the temperature according to our requirement, according to the characters of the matrix. Next factor that can affect the overall extraction efficiency is the pressure. Now, as I told you that pressure is something which is required to keep the solvent in the liquid state whenever we are exposing that solvent at a temperature far above the atmospheric boiling temperatures. So this increase in pressure will help you or will help us in avoiding the phase transition of the solvent. I have taken an example of N-hexane, and we know that N-hexane is a highly volatile, highly non-polar solvent, and its atmospheric boiling point is 68.7 degrees Celsius. Whenever this hexane is subjected to 290 psi pressure, then the boiling point of this hexane increases to 209 degrees Celsius. So you can retain the liquid nature of hexane at a temperature of 209 degrees Celsius if you increase the pressure to 290 psi. So this is how the pressure helps in keeping the solvent in the liquid form. It has further been observed that pressure does not impact on the leaching of the solutes by the solvent, but it enhances the penetration of the solvent into the matrix, because you are applying the pressure, so it will enhance the penetration of the solvent molecules into the plant matrix, but it will not affect its leaching out of those solute molecules. Further, overpressure has also been found to reduce the time that is required to fill the extraction cell with the solvent or with the sample, because we are filling up the extraction cell with solvent or sample, and we have to achieve a uniform filling of the extraction cell. So this increase in pressure also help in reducing the time to achieve that goal. But many a times it has also been observed that if the system is exposed to overpressure conditions, then the sample bed that is formed in the extraction cells becomes very compact. And once the matrix bed becomes compact in the extraction cell, the back pressure of the solvent increases tremendously, which will add up additional burden on your system. So again, the bottom line is one has to be very critical regarding the pressure condition also, and we have to optimize the pressure condition as per our requirement. It has also been observed that increase in pressure changes the overall properties of the sample also by decreasing the active site. Again, this happens when we increase the pressure beyond the optimum limits, and once the active site are decreased in the sample, the overall extraction efficiency decreases, because now the sample will not be able to interact with the solvent, and solvent will not be able to solubilize the solute molecules. So again, optimum pressure is the most required thing in the PSC or ASC type of extraction. Next factor that will affect the extraction efficiency is the type of the solvent, and it has been observed that wide variety of solvents can be used in accelerated solvent extraction or pressurized solvent extraction. We know that I told you in my previous lecture that the solvents that can be used for oxalate extraction, for specified secondary metabolite or for specified solute extraction from a matrix, those solvents or the technique, oxalate technique that has been approved by the regulatory agencies, same solvents can be used in accelerated solvent extraction. But there are certain exceptions, and those solvents whose auto ignition temperature is in the range of 400 to 200 degrees Celsius, they cannot be used in this technique, because I told you that in ASC or PSC we increase the temperature up to 200 degrees Celsius, and if a solvent ignites itself at that high temperature, we cannot use that solvent. And the most common examples are diethyl ether, carbon disulfide, or 1,4-dioxane. Such kind of solvents cannot be used for ASC or pressurized solvent extraction. Further, the solvents which have very low polarity like hexane, they also cannot be used for extracting out by using this particular technique. As we discussed that by increasing the polarity, by increasing the temperature, the dielectric constant of the solvent decreases, because with the increase in temperature certain particular or the molecular changes occur which decreases the overall dielectric constant, and therefore a solvent which is known for solubilizing polar constituent will be able to solubilize non-polar solvents. On the other hand, if a solvent itself is a non-polar, then we are not gaining anything by subjecting that solvent to increased pressure or temperature conditions. So therefore, low polarity solvents are also not used in ASC. Apart from these, we should also avoid use of strong acids or bases in case of pressurized solvent extraction. But yes, there are certain extraction conditions where we require the change in the pH, because we know that pH plays an important role in certain extraction processes wherein the solute molecules are sensitive towards pH changes. So in such cases, if you have to use either acid or base, then dilute acids or weak bases should be used. But yes, strong acid and bases should always be avoided because of their obvious corrosiveness to the system. Then non-toxic, non-residual organic solvents such as ethanol or acetone, they are normally preferred for this kind of extraction technique, because I told you that we are moving toward greener techniques, or we are moving toward the use of greener solvents which are safe towards environment, which are safe to the user. Therefore, ethanol, acetone, such kind of solvents are now more preferred in the extraction techniques. Whereas the toxic organic solvents like dichloromethane, acetonitrile, or any other medium polar solvent, they are also used in ASC for specific reasons. If your sample requires the use of these kind of solvents, then yes, you can use these solvents. We can also use such kind of solvents in mixture to further modify the properties of the solvent, to further enhance the solubilizing power of these solvents. We can also use water alone or in mixture with other solvents like methanol or ethanol, obviously in specified proportions. We can also use their combinations. And I told you that whenever we are using water alone, then the technique is known as subcritical water extraction, because during this process we are exposing water at around 200 degrees Celsius and at a specified pressure value, and such conditions are considered as subcritical conditions for water, and therefore this technique becomes subcritical water extraction. So water can be used along with the other solvent mixed in a specified proportions. We know that pH plays an important role in the extraction, and as I told you that if the change in pH is required to extract out specific solute which are pH sensitive, then obviously we should go for use of weak acid or base as per our requirement. Obviously strong acid and strong bases should always be avoided. Next factor is the additional additives. Now, as I told you that water alone can be used, or it can be used in mixture of other solvents, and when these other solvents are used, we call them as modifiers. And these modifiers, as I told you, can be methanol, ethanol, acetone or acetonitrile, and their proportion is normally considered to be 5%. And once these solvents are used with water, they change drastically the dielectric constant of water, and we can change the polarity of water from highly polar towards non-polar by avoiding the drastic increase in the temperature. as I discussed in that figure, if you increase the temperature of at which water is exposed to 500 degrees Celsius, then water will have same solubility properties, same solubility characters as that of hexane. So if we are using modifiers like methanol, ethanol at a concentration of 5%, then we can achieve that decrease in polarity without drastic increase in the temperature. Apart from the environmentally safe solvents or water, we can also use certain surfactants, or which are also known as micellar liquids. And the most common example one can remember is Triton X100 is the micellar liquid or a surfactant that has shown efficient, or I will say that has shown very good results when it is used in ASC. It has been found that this Triton X100 has almost similar kind of extraction efficiency as that of methanol. So obviously we can always go for surfactant liquids because they are much safe in comparison to the organic solvents. Now this micellar mediated extraction, wherein we are using certain surfactant solutions, this also help in controlling the degradation of certain compounds in comparison to the organic solvents when they are used in PSC or ESC. Because these micellar surfactants have both amphiphobic or amphiphilic type of properties, wherein they help us in solubilizing or in extracting out non-polar as well as the polar constituent. Therefore, they does not cause, or I will say we will not increase the temperature to a much higher level whenever we are using micellar mediated liquids or the solvent for extraction purposes, thereby decreasing or avoiding the degradation of the compounds. Now apart from these surfactant liquids, ionic liquids are also used in PSC. Now ionic liquids are nothing but these are the molten salts which appear in liquid form at 100 degrees Celsius or above. Now these ionic liquids, they are becoming solvents of choice because of their specific properties. These are chemically and thermostable, these are highly non-volatile, and they have almost similar kind of solubilizing properties as those of organic solvents. So once we get a solvent which is quite thermostable, which is quite chemically inert or chemically stable, I will say, or which is less volatile and has equivalent solubilizing properties as that of the organic solvent, then we don't have to increase temperature to very high levels and we can achieve extraction even at say below 200 degrees Celsius. So that is why ionic liquids are becoming solvent of choice, and I will discuss ionic liquids in detail whenever I will discuss different types of solvents that are required for extracting the natural matrix. Now during extraction there are certain constituents which are vulnerable towards oxidative damage or oxidation, by which they are degraded. So for such type of constituents, certain antioxidant compounds are also added like ascorbic acid or butylated hydroxytoluene, which is also known as BHT, and these antioxidant compounds prevent the oxidative degradation of those solute molecules. Apart from these, sometimes carbon dioxide is also added in order to decrease or in order to lower the pH of the water, because I told you certain solutes are more sensitive towards the pH condition, and if you require slightly acidic conditions for the extraction, rather than using a weak acid, we can also add carbon dioxide to water to decrease its pH. Now apart from all these additives in the solvents, we also use certain dispersing or the dehydrating agents in the during the extraction. As I told you, the presence of moisture basically has a negative impact on the overall extraction efficiency of the process, and therefore dehydrating agents are added. We also discussed that dispersing agents help in filling up the voids, filling up the empty spaces, thereby reducing the overall volume of the solvent that is required to extract the drug. And I gave you an example of dehydrating or dispersing agent as hydromatrix. Glass beads can also be used as dispersing agents, and so on and so forth. So friends, in the next lecture, I will be discussing with the other parameters that can affect the PSC, and we will also discuss the applications of this technique. Thank you.